Hello viewers, my name is Jordon Johnson and I am speaking on behalf of my fellow authors, Emily Hindalong, Giuseppe Carenini, and Tamara Munzner, to discuss our work on identifying abstractions to support the development and assessment of visualizations of stakeholder preferences in group decision-making scenarios. Group decision-making, or GDM, situations arise when multiple individuals must collectively choose from among a set of alternatives. Such scenarios are ubiquitous in collaborative efforts and can vary wildly in terms of the complexity of the decision and the impact it may have on the group or larger community. The decision process can be incredibly complex, whether due to the number and features of the alternatives being considered or due to the inclusion of multiple decision makers with potentially conflicting points of view. Organizations often fail to enact positive change because they lack the resources to tackle these complexities. One approach to group decision-making that is grounded in the literature includes the step of having stakeholders explicitly model their preferences over the alternatives. The decision makers can then examine those preferences, which is an activity we call preference inspection. Ideally, this preference elicitation and inspection process should be iterative, since insights that are gained from the inspection process may result in modified stakeholder preferences, which can then be elicited anew. The preference inspection process can be supported by effectively designed visualizations, since they take advantage of the powerful pattern recognition and pre-attentive capabilities of the human brain. However, while powerful design models exist for visualizations in general, such as the nested model of visualization design, no framework has previously been developed specifically to guide the design and assessment of visualizations to support preference inspection. In this work, guided by the nested model, we have developed such a framework, consisting of data and task abstractions that are applicable to GDM in general. A key feature of our framework is a novel preference model taxonomy that organizes preference models into a hierarchy of classes. Our framework can be used to assess and guide the design of preference visualizations. We began with a collection of 7 widely varying GDM scenarios and identified their data and features. Each scenario was summarized, addressing the following points. First, the decision problem and decision-making process. Second, the data and preferences modeled in terms of multi-criteria decision analysis. Third, the goals of preference inspection and how they are achieved. From our analysis of GDM scenarios, we were able to identify a number of abstractions related to what kinds of entities may be included. Let's consider the example of choosing a hotel. The first and most obvious abstraction is a set of alternatives, such as the Hilton or Marriott. Each alternative has a set of attributes which may be objectively assessed, such as bed size, or subjective, such as mattress quality. These attributes may have different weights for each stakeholder, since some may value the quality of the Wi-Fi signal more than the quality of the bed. Attributes may be hierarchically organized. For example, bed size and mattress quality may be components of a more general attribute for room quality. Any objective attribute should have a domain of possible outcomes, and a mapping of alternatives to these outcomes. For example, one hotel may favor larger beds. Another abstraction is the set of evaluators, from whom the preferences are to be elicited. These are commonly a subset of the stakeholders in the decision, such as the people who will be staying at the hotel. Each evaluator has a preference model for the alternatives and attributes being considered. These evaluators may be grouped according to background or role in the decision. The evaluators may also be assigned weights based on their qualifications to assess the alternatives, their share in the decision, or some other facet. A preference model is a quantitative description of an evaluator's preferences over alternatives or attributes. Several types of preference models have been cataloged, but there have been few attempts to relate these models to each other conceptually. We propose a novel taxonomy of preference models that captures the relationships between several types of preference models likely to be encountered in GDM, so that a comprehensive data model for visualizing preferences can be created. Our taxonomy organizes preference models into a directed graph of classes. Each class is defined based on, first, whether evaluators assess alternatives, their attributes, or the outcomes those attributes may have. Second, whether these elements are scored or ranked. And third, whether attributes or outcomes are assigned weights. A key feature of the taxonomy is that it is possible to move between these classes by applying transformations to the data. This graphical representation indicates that ancestor classes implicitly encode their descending classes. In order to express our data abstractions in the language of visualization, We map sets, such as alternatives and attributes, to dimensions, and functions of those sets to measures. The measures may include rankings, scores, or weights supplied by evaluators, as well as evaluator weights and objective attribute outcomes for each alternative. The measures used will depend on which preference model is employed. With data abstractions in hand, we turn our attention to developing abstractions for the analysis tasks used in preference inspection. We first coalesced the scenario-specific goals identified in our initial evaluation of the GDM scenarios into a hierarchy of scenario-independent goals and sub-goals described in qualitative language. Examples of high-level goals include discovering viable alternatives and discovering sources of disagreement. We were then able to relate the tasks coded in our evaluation of the scenarios to abstract tasks that are widely used in the visualization literature. In this way, we identified a total of 34 visualization tasks related to preference inspection. The task inputs and outputs are entities defined by our data model. An important application of our abstraction framework that we explore in our paper is the ability to assess visualization designs. We examined a number of existing preference visualization tools and prototypes. We were able to identify which preference model classes they were designed to support, and from there we assessed how well each one supported the analysis tasks related to those classes. The primary limitation of many of these tools seems to be that of a narrow scope. With our framework of data and task abstractions in place, it is hoped that future designs will be able to consider and support a more comprehensive set of analysis tasks. Another important application is the development of guidelines to support the design of preference visualizations. We recommend that designers first identify the preference model classes to be supported by their systems. They should consider questions such as whether their alternatives will be evaluated directly, or if the evaluation will include their attributes. Once the preference model classes are identified, designers should consider whether downstream classes within the taxonomy should also be supported. Designers should also consider stakeholder dynamics. Relevant questions include whether stakeholders are equally important in the decision process and whether they can be grouped by background or group role. Once the relevant preference model classes have been identified, the corresponding subsets of the data and task abstractions can be examined. Priority for task support can then be determined by considering whether the tasks are equally important to the decision domain. Having identified the tasks to be supported, visualization idioms can be selected based on how well they support those tasks. It is also important to consider other logistical features of the decision scenario, such as whether the decision makers are co-located and whether the decision process will be synchronous. Such considerations will determine where, when, and how the visualizations will be presented to the decision makers. In conclusion, we have created comprehensive data and task models for preference inspection in group decision scenarios. A key component of these models is a novel preference model taxonomy. Our abstractions form a framework that can be used to assess or guide designs for preference visualizations. Important future work includes integrating our framework with other aspects of group decision support. For example, integrating preference visualizations with geolocation or other logistical data. Future work also includes fleshing out the framework by considering the goal of discovering nuances that have not been captured by existing preference models. This may include promoting discussion and eliciting textual feedback.